The more secure approach would be to either ignore it or to come back and say that is not a valid username password combination. So the exact right thing to do can vary, but generally you want the event or event condition combination to be handled in some way that makes sense, and the processing would continue on normally from that point. So it would not have some abnormal termination that would happen a few seconds or minutes later as a result of this weirdness having occurred. Okay, now sequences of events. Moving on to this issue of testing of sequences of events. There is this concept of what's called switch coverage. Now, things get a little bit complicated here, potentially. Try to keep this fairly straightforward. Switch is basically just another way of saying transition. And the person who defined this, a professor named Chow, for some reason picked the name switch rather than transition. I guess he liked it better. Now, Chow did something else weird, which was instead of referring to switches as the number of transitions, he subtracted one. So if you're going to cover all transitions of length 1, then that's called zero switch coverage. Why? That's what Chow said. That's why he called it zero switch. I don't know why. Obviously, this would have been more comprehensible if you called it one switch for one transition long and two switch for two transition long, but he didn't. So zero switch refers to covering all transitions of length 1. One switch refers to covering all transition sequences of length 2. Now, they have to be possible combinations of transitions. Okay? And so what we're going to do to try to identify the possible combinations of transitions, and by possible I mean here defined on the diagram. Okay? So in other words, we're not going to try to do transitions of length 2 or 3 or whatever that include invalid stuff. That was what the table was for. So what we can do is define a table. Now, the number of rows in the table corresponds at most to the number of states in the diagram. Okay? So here you see, whoops, yeah. This is the A row, B row, C row, D row, F row. Now you might be saying, well, what happened to the E row? Well, the E row has no outbound transitions. Once you get into the E row, it's like the Roach Motel of the state transition diagram. You check in, but you don't check out. You're there, right? Okay? So you won't need a row in the table for any such state, because any transition that goes into that state, there won't be any exiting transition from it. Okay? So we can leave out the E row. So we have, in this case, 5, which is less than 6. So the number of rows in the state and switch table will always be equal to or less than the number of states in the state transition diagram. The number, well, let me back up just a second. There are two halves or two parts to the switch table. There is the zero switch part, and in this case, the one switch part. If we were trying to cover all transitions of length 3 or longer, then we would have a third part to this table, which would be the two switch columns. Okay? But because we're interested in this particular example in one transition length sequences or two transition length sequences, we're just going to have zero switch and one switch. Now, in any switch table, the zero switch part of the table will have the number of columns equal to the maximum number of outbound transitions from any of the states. Okay, so in other words, any state, you look at every state, you determine how many outbound transitions there are for that state. The number of states with the maximum number of outbound transitions is going to determine how many columns you have in the zero switch part of the table. Okay, in other words, we've got to make the table wide enough that we can include all of those. Now, to generate the contents of the zero switch side of the table, you redraw the diagram with the states relabeled as letters, as shown here, and the transitions given unique numbers. It does not matter which letters you choose for the states, nor does it matter what numbers you assign to the transitions, as long as both the states and the transitions are labeled uniquely. I would recommend using the states are letters and transitions are numbers convention here, because this makes it very regular in the way it works and compact. So I think that works very, very nicely. So what you can see here in the A row of the zero switch part of the table, we have A1. See that? A1, that corresponds to this guy here. A2, which corresponds to the abandoned, going over here to the E, and then A9, which is that, and that's all of the outbound transitions for the A state. Right? Similarly for B, there's B8 and B10 and B3, so those guys are all here. Yeah. For the C state, we have C14 and C11 and C4. Right, those are all here. And for D, we've got 13, we've got 5, and we've got 12. Those are all there. And then for F, there are only 2 outbound, so there's F6 and F7. Okay? Now, notice that at the end of each one of those zero switches, we are going to be in a state. Now, I haven't specified the state in the table, because you don't need to. It's implicit, right? Once you do A1, for example, you're back in A. You know that because you did A1. Okay? So, now to generate the one switch side of the table. Basically, because the maximum number of outbound transitions is 3 from any given state, in this particular example, the one switch part of the table needs 3 squared columns, right? Because if we leave a state that has 3 possible outbounds and we land in a state that has 3 possible outbounds, then the maximum number of combinations there across those is 9, 3 times 3, okay? So what I've done here is I've broken this up. I've got 9 columns, and I've broken it up into some nice groups of 3, each one corresponding to where I land from the initial starting zero switch. Okay, so take a look. A1. The first 3 here correspond to the different things that could happen with A1. Okay, so I could go A1, A1. That's 2 transitions long, and there it is. Or I could go A1, A2. All right, 2 transitions long. There it is. I could go A1, A9. That's that. Now A2, be nice and regular here. A2 drops me into E, and nothing can leave from there, so there are no one switch entries in the one switch side of the table that correspond to the A2 column in the zero switch side. See? Because once I get into E, there's no outbound. Therefore, there's no sequence of transitions of length 2 that starts with A2. A9 is a different story. A9 drops me into B. Okay? So, what happens when I drop into B? Well, let's see. I already know, actually, what happens when I drop into B. I don't even have to go through it again, as I did